Similar to our last example, we're going to determine all values of r such that y equals e raised to the rx power is a solution of the constant coefficient equation y double prime minus 5 times y prime minus 24y is equal to 0. With that in mind, we'll start this one the same way that we started the last one, which is to recognize that we have a second order differential equation. So let's take a couple of derivatives. Derivative of e to the will be e to the, and then the chain rule says multiply by the derivative of the rx that we see in the exponent. So r times e raised to the rx power. Taking a second derivative, the chain rule will give us a second factor of r, giving us r squared times e raised to the rx power. Now if I take all of these and I plug them into the original differential equation, I will wind up with the following: y double prime r squared times e raised to the rx minus 5 times y prime, which is r e to the rx, minus 24 times the original function e raised to the rx power. And the original differential equation has this all being equal to 0. First thing I notice is that all three of the resulting terms here have an e to the rx in common. I'm going to go ahead and factor that out. When I do factor it out, what I'm left with is r squared minus 5r minus 24. As we did on the previous example, this factors pretty nicely. The two factors that I would be looking for would be r minus 8 and r plus 3. According to the factor theorem, this means that the two solutions would be r is equal to 8 and r is equal to negative 3. This is technically as far as we would need to go with the problem. However, we can also take it a step further and say that the solutions will be y1 is equal to e raised to the 8x power, and y2 will be e raised to the negative 3x power. We obtain these by taking the values of r that we just got and plugging them back into the original assumption, which we can see right up top, y equals e raised to the rx power. In terms of linear algebra, we would be saying that these two are two linearly independent solutions of our original differential equation.